Okay, so a question you may be asking yourself is Markovnikov's rule always true? Does every reaction in organic chemistry follow Markovnikov's rule? And of course, the answer is no, because that would be way too easy. So let's talk about a reaction where Markovnikov's rule does not hold. We're going to talk about a few of them over this video and the next couple. But the first one is hydroboration. Hydroboration is the addition of hydrogen and boron across a double bond. So we're going to do another addition reaction. I'm going to use this one, this alkene. Our conditions for this one are borane THF, BH3 THF, and sodium hydroxide and hydrogen peroxide. So another two-step reaction. This is one of those where there's a lot of stuff in here that doesn't really react. The only thing that we're really going to be interested in is this BH3, right? That's the thing that we're really going to follow. The product of this reaction does not follow Markovnikov's rule. So instead of having the hydrogen on the less substituted, we end up with the hydrogen on the more substituted and the oxygen on the less substituted. So this is what we call anti-Markovnikov, which it is not really, Markovnikov's rule is still correct. It's just that in this case, there is no cation in the mechanism. And so if we never form a cation, that means there's nothing for, we're not dealing with the same kind of idea where the oxygen is going to come in and attack the carbocation. So there's no carbocation in the more substituted position. Different rules apply, right? So what's going to happen in hydroboration is when we have our alkene, so I'm going to redraw our alkene over here, it's going to react with BH3. And I'm going to draw BH3 like this, right? So we have BH2 and an H. You may be wondering about the THF. BH3, THF is just a solvent, and BH3 and THF form a complex together that's not super well understood. BH3 on its own is very, very unstable, but if you make a complex with THF, then you can put it in a bottle and store it. And so this usually gets sold as a complex of BH3 THF, but BH3 is the only thing that reacts. So the difference in this reaction versus the previous ones that we've seen, it looks like we're setting up for another alkene plus acid to make a carbocation, except in this case, we're going to make both sigma bonds, two new sigma bonds are formed at the same time, right? So we call this a concerted mechanism. Okay, so this could be good news, right? That means our mechanism is simpler. There's fewer steps in it. So previously, whenever we reacted an alkene with a strong acid, we have multiple steps. Alkene reacts with acid to make carbocation. Then carbocation rearranges, or it doesn't. Then conjugate base attacks carbocation, right? So we have a lot of kind of thens, right? This happens, and then this, then this. And sequentially, we go step one, step two, step three, right? Make the carbocation, check for rearrangement, bring in the conjugate base. And all of them are kind of the same, but it's 3 steps that we have to do to get from starting material to product. 4 steps if we have to get rid of an H plus to make the thing neutral again, right? So there's a lot of steps. With concerted mechanisms, everything happens at once. And so we draw this all in one go. The hydrogen comes in and attacks the carbon. The pi bond comes out and attacks the boron. And we make 2 new sigma bonds all in one go. We break our pi bond as well. And so we get out the hydrogen on the less substituted carbon and the boron on the more substituted carbon. This always happens, right? Hydrogen always goes on the more substituted carbon. And the reasoning behind this is that because we're doing this all in one go, that means that we're kind of creating a crowded reaction area. right? The pi bond is right there. The boron is here. The hydrogen is here. All of them have to come together in kind of this exactly perfect way to make all these bonds form in one go, right? So it's a really organized transition state. It's a really organized setup for this mechanism to occur. And what that means is that the boron is the biggest thing in there, right? The boron is bigger than the alkene, it's bigger than the hydrogen and all that. And so the boron tries to find the most space that it can. It tries to minimize its steric repulsion. You remember steric repulsion from back in the first unit, right? So the more electrons that are surrounding that boron, the less stable it's going to be because the more steric repulsion it's going to have. So the way that it minimizes that is, of course, the boron attaches to the less substituted carbon. This carbon doesn't have as many things attached to it. There's not as many electrons around. And so the boron always goes on the less substituted carbon. Just like we said with the hydrogen going on the more substituted carbon, right? So those two things are, of course, related. Goes on less substituted carbon. All right. And that does it. We've done our addition. We've broken the pi bond. We've made 2 new sigma bonds. Hooray. Everything is good to go. Step 2 of this reaction, the sodium hydroxide and the H2O2, this mechanism, a lot of textbooks go through this mechanism. I've never found any reason to go through this. All that we're doing here is we're replacing the boron with OH groups, right? That's all you need to know. The mechanism for this has nothing to do with additions. It has nothing to do with substitutions. It has nothing to do with eliminations. And so it really doesn't fit in what we talk about in this course. So it's safe to say that we can replace boron with oxygen under these specific conditions, sodium hydroxide and hydrogen peroxide. So I guess the big difference here in hydroboration is that it's an anti-Markovnikov reaction. The boron goes on the less substituted carbon, which means that the oxygen ends up on the less substituted carbon, right? We now have 3 different ways of making alcohols from alkenes, right? So if we look at I'm going to use this same substrate, right? If I look at this substrate, depending on what I react it with, I can make 3 different alcohols. Right? And I've done all of these examples in the last couple of videos. First of all, we can react this with H plus and H2O. Right? This will follow Markovnikov's rule and we'll get a rearrangement. So we'll get the OH on the tertiary position. Markovnikov's rule plus rearrangement. We can do oxymercuration, right? Mercuric acetate, H2O, and then step 2, sodium borohydride. That'll give us the Markovnikov's rule will still be followed. No rearrangement, right? So let's draw a line here to keep things separate. No rearrangement. And now we have hydroboration. BH3THF, H2O2, sodium hydroxide, and we get another alcohol where we end up with the oxygen on the less substituted position. This is anti-Markovnikov. We don't have to worry about rearrangement because, of course, we never make a carbocation anywhere in this mechanism, so there's no opportunity for rearrangement to occur. So the only time we have to worry about rearrangement is when we use strong acid. So when we use H plus H2O, we have to worry about rearrangement. But notice that we can get an alcohol in the primary position, the secondary position, or the tertiary position of this particular alkene, depending on what conditions we choose. So we have 3 different ways to make 3 different alcohols.